Actually, since I started my company, I don't get out much, so it's very nice to be here. Thank you. So, this is the first publication of the space elevator. It was published in Pravda, the old Soviet Union's newspaper, in the children's section in 1960. And this is in Russian, but I've read the translation. You can tell that the guy who published this, Yuri Artsutanov, knew what he was talking about. And what he's doing is he's telling children this is how you're going to get into space. And Yuri Artsutanov published here because his father had been branded an enemy of the Soviet Union, and so his engineering career was suppressed, and he found it very difficult to publish in Soviet journals. So it doesn't have anything directly to do with the space elevator, but I really want people, especially students, to think about this. And that is that in the 9th of October, an editorial appeared in the New York Times that said, in part, this is just a small part of it, the flying machine which will really fly might be evolved by the combined and continuous efforts of mathematicians and mechanicians in from 1 million to 10 million years. On the same day, in Orville Wright's diary, it says, we started assembly today, and that was of the Wright Flyer, which they then flew 2 months later for the first time. So, don't believe everything you read in the newspaper. So the basic concepts start here. When I talk about a space elevator, what I'm talking about is a carbon nanotube ribbon stretching from the equator of the Earth 100,000 kilometers out into space to a counterweight, which we call the apex anchor. The way this works is you start at the Earth and you ascend the ribbon by climbing it to geosynchronous. There, you're climbing against gravity, and of course gravity decreases as the outward force and gravity start to sum to zero right here. And then beyond that point, it's actually an outward force that builds up. So you have to break beyond geosynchronous to get farther out here. There is also a restoring force. Once that elevator is perturbed from its equilibrium position, there is a restoring force to bring it back. Otherwise, we wouldn't be talking about it because unstable equilibrium is not something we spend time on. So this is low Earth orbit. This is where we all go now, our astronauts now go. The Apollo astronauts, of course, went all the way to the moon, which is much farther than the end of the counterweight. But right now, that's where all of our destinations are. And GEO is way out here. And if you want to get into low Earth orbit using a space elevator, you want to use mostly energy from the space elevator. So you climb all the way up to like at least 14,000 kilometers. Then when you drop into a highly elliptical orbit by leaping off the elevator, you miss the atmosphere of the Earth. And going higher gives you higher elliptical orbits, and you circularize your orbit using a small rocket motor. So most of the energy comes from the space elevator. And if you want to go beyond low Earth orbit, you have to go to the moon, Mars, other places. You can get a delta V by coming way out here and letting go. All the way out here at the counterweight, the delta V you get from a 100,000 kilometer space elevator is around 7.7 kilometers per second. That'll throw you beyond Venus to the inner solar system, but not all the way to Mercury. And it'll throw you beyond Mars, but not quite to Jupiter on the outer solar system. So this is an excellent graphic from Discover magazine. Years ago they did an article on space elevator, and they produced this. So this is what got a lot of people interested in the space elevator. That shows multi-walled carbon nanotubes. If you look at the original publications of the space elevator, especially the ones done by the American inventor, Jerome Pearson, he did the physics of the space elevator, and he says in this is a very interesting academic exercise. We have nothing strong enough to make an elevator on the Earth. So people were well aware that we didn't have anything strong enough and light enough. But the material scientists who started researching this and started doing theoretical calculations on its ultimate strength started to realize this could be used to make a space elevator. Here is a ground station. It's a floating platform in the ocean. We have the ribbon going up here, or the tether, and here we have a power beaming station. It's very important that the space elevator does not carry its own fuel, that it gets power beamed to it as it climbs. Here is an artist's conception of 4 climbers on the elevator, each being supplied infrared laser energy. Here's a inset of the photovoltaic array on the bottom, which is receiving the power to drive the motors. And this is an artist's conception of the space elevator climber reaching the counterweight, which is the spacecraft that first launched the pilot ribbon. And so now I want to talk about why we would do this. Because anything we do beyond rockets is really, really hard. And if we really want to go out into the solar system, I think we have to do something besides rockets. So the space elevator breaks the rocket paradigm. And I'll have a little bit more to say about this later. Because the space elevator climbers does not carry their own fuel, then the power beam from the Earth, that's very important to unload that mass. The economy of scale of elevator operations, we expect it to be more like a railroad. Really high initial cost to lay the rails, to put up that tether, but then running things across it is relatively inexpensive. And to get into orbit, as I've said, you have to lift the payloads very high, so remember that, because that's different. Sometimes eminent scientists will criticize the space elevator because they don't know that. So, chemical rocket technology is actually very mature. Years ago I was at a conference and a young rocket engineer it's almost like an old-time revival in the US. He was pounding the table, put billions of dollars into rockets. We can get that last amount of, of performance out of rockets. And at the end I asked him, I was the first question, I said, what kind of improvement? He said, we can get 15% more performance out of rockets. And I agree with that, but I'm not looking for a 1.15 factor. I want a factor of 10 in performance. I want a factor of 100 if I can get it in performance. And so rockets are not going to get us there. And reusable rockets, which I think are very important, we should also do those. That technology, fully reusable, doesn't yet exist. And in fact, there are problems with it. You can ask me questions at the break if you want about that. And this is an old slide because of Elon Musk. It's an old slide. $10,000 per kilogram is the round number we use. He's probably dropped this down to 7,500, but that's kind of what I use. And I want to remind everyone that to take a test mass, like a 1 kilogram test mass from the surface of the Earth up to low Earth orbit, or even to twice that energy, which is to escape velocity, it takes around 17.2 kilowatt hours to do that. And that's like $2 worth of electricity. So it's not, so that test mass doesn't get a lot of change in energy going from the surface of the Earth all the way up to low Earth orbit. But in order to wrap a rocket around it and actually take it there with chemical energy, then it costs 4 million% more in energy and cost. And this is the reason. So this is the rocket equation. So the change of velocity you need to go somewhere is the propellant velocity, the velocity of what's coming out the nozzle, times the log of the initial mass to the final mass. So the initial mass you can think of as fuel, and the final mass you can think of as payload. If rocket engineers did everything perfectly, they'd have all fuel and then all payload at the end. And physically, what's happening is you're raising large amounts of fuel high in the atmosphere so you can burn it to continue to raise large amounts of fuel high into the atmosphere and burn it so that you can then accelerate the payload into space. And you could burn all the fuel on the launch pad like an artillery shell does, but most things, humans and most delicate pieces of equipment like spacecraft, can't survive the 10,000 Gs or whatever, 5,000 Gs that occurs. In World War II, we started putting electronics in shells for proximity fuses. But that was very specialized, and it could take thousands of Gs. We humans are not going to go up on an artillery shell. So the Saturn V is my favorite rocket, and it kind of illustrates all this. 5% of the mass of the fully fueled rocket got to low Earth orbit. And then they burned a bunch of fuel, and 2.4% of that mass went to translunar injection, and so went on to the moon. Now, the first stage had a 94% mass ratio. Does anyone know what that means? It means that 94% of the mass of the first stage was fuel. The rocket engines, the structure, the tanks, the staging equipment, that was all 6% of the mass. So it's very important to minimize the mass of your rocket and increase its fuel capacity. It was the most powerful rocket ever flown. It had no major failures. I went to a space conference years ago, and the old guy stood up and said, I was a young engineer on the Apollo program. My group did the reliability calculations. All of our calculations showed we would lose half the missions. And I said, we have to stop. We're going to kill half the astronauts. They said, we're not going to stop. And he said, the reason why we did so well is because the Saturn V had no failures. They expected it to fail at a much higher rate than it did. And of course, so the thing to remember about this is I'm using my $10,000 per kilogram. I'm raising up the test mass to low Earth orbit, then I'm going to raise up the fuel it takes to get that test mass to Mars, and it comes out to be at least $33,900 to move a kilogram from the surface of the Earth to Mars. And my house is worth about 10 kilograms. So if we're going to be setting up colonies on Mars and everything, we're going to be sending a lot of treasure to do that. And so I think we need something much more efficient. Nuclear rockets would be a great step forward. In fact, in the 1970s, the Los Alamos National Laboratory, where I used to work, and NASA, they were ready to do a full-up mission test. You know, just build a rocket and put it into space, and they were canceled. The nice thing about the nuclear rocket is that the propellant velocity, even in the simplest nuclear thermal rocket, is 2 to 3 times greater than for the best chemical rockets, liquid oxygen, liquid hydrogen. And if you could do fusion, you might even get 30 to 300 times this delta V, this propellant velocity. So it enters linearly in the delta V calculation, so it would be a great boon to space exploration. I believe you build a chemical rocket, you throw it to your destination with a space elevator, and the nuclear rocket brings you home. That's the way I think we may settle the solar system. So let me briefly go through some of the history. Konstantin Tsiolkovsky, the Polish academician who was living in Russia, first derived the rocket equation, and he went to in 1895 he went and saw the tallest structure in the world, human-made. Does anyone know what that was? Yep, it was the Eiffel Tower. It was the World's Fair in Paris. And he imagined that stretching all the way up into geosynchronous orbit, which is something he'd already derived and found out about when he was doing his calculations on orbits and that. Then, of course, the famous science fiction author, Arthur C. Clarke, in 1945, he patented the concept of the geosynchronous satellite. And Yuri Artsutanov published the article in Pravda. And then Jerome Pearson actually published the physics of the elevator in 1975, and he had a hard time getting it published. It took him years to get a serious scientific journal in the United States to publish the space elevator stuff. So, one of the ideas, of course, was in Arthur C. Clarke's science fiction book, Fountains of Paradise. And here's how he saw a space elevator being built. Step one, you capture an asteroid and put it into geosynchronous orbit. Then you go up there on that asteroid and you start using the carbon in it to build some kind of really strong carbon tower. And he did guess right that it was carbon tower, down toward the Earth. And it gets thinner and thinner, and finally it touches. So this is a massive structure, and then you climb up it with different climbers. Now, in 1999, NASA had a workshop because of the 1991 discovery of carbon nanotubes. And they said, this will take 300 years to do. And I agree with them, because it would take 300 years to convince astronomers to let something this big, that close to the Earth. I think it would be too dangerous to do that. So a colleague of mine actually started a series of studies, and he wrote a book about His co-author, Eric Wessling, took his results from his studies and wrote the Space Elevator book in 2002. I think it's still one of the best references. It's written for a public audience, but he does pretty much go through most of the major components of Space Elevator and talk about them and how he would solve the problem and how we could. So he came up with a conceptual design. And we've had many, many conferences. Just a month ago, we had our 2018 conference near Seattle. In 2019, we'll have another one. The IAC has a track here in Bremen. On October 4th, there'll be Space Elevator people there giving presentations. And the National Space Society, which is the largest space group in the United States, has a Space Elevator component. So I want to talk a little bit now about the design of the Space Elevator. So in principle, you can design a Space Elevator out of anything. And if you did high-strength steel, then it would end up being, you see, it'd be more massive than the universe. And that's the problem. So what we really need is something very strong and very light. And that brings us way over here to carbon nanotubes. So this is what we feel we need to build a practical space elevator. Now this calculation breaks down anytime the elevator gets anywhere near the mass of the Earth, but it does kind of illustrate the point. And carbon nanotubes are the long pole in the tent. The material is the problem. They were discovered in 1991 by E.E. Jima. He recognized how they were related to buckyballs with the C60 structure. They're 1 to many nanometers wide. Almost all of the ones that are made commercially are just few microns long. The record from a very heroic experiment in a laboratory is actually 55 centimeters. It's actually remarkable. But they can only do a few of those at a time, so it'll never be commercializable. The strength is up to 300 gigapascals, theoretically. High-strength steel is 4 gigapascals. And of course, they have 1/6 the mass. So we're hoping to get a macroscopic tether for the space elevator that has at least 130 gigapascals of strength. And that's what we'd like to have. Now, there's a big problem with carbon nanotubes, and that is that they were discovered 27 years ago, and they have pretty much failed to live up to their promise. And the reason is because of the way they're synthesized. Almost all commercial carbon nanotubes are made with chemical vapor deposition. This is one of the most successful chemical processes ever. It's used all over the place. It's used in electronics. It works fantastic, but it doesn't work well for carbon nanotubes. This is very controversial, me saying this, because if you ask someone who uses chemical vapor deposition to create carbon nanotubes, he'll tell you there's no other way. He'll say that I'm wrong, there's no other way. And everyone else believes him too. Over the last 26 years, $35 billion of research and development has been poured into carbon nanotube research. And now they only have a $0.7 billion a year industry. It's mostly just adding these cheaply produced carbon nanotubes into some kind of a matrix material, mixing it up, and you get like a 10% strength in the increase in the matrix material. So you're not exploiting any of the fantastic properties of carbon nanotubes, and that's why it's such a small industry. The problem with chemical vapor deposition was explained to me during a presentation by Benji Maruyama, the Air Force Research Lab. He started the talk by saying, my team has spent 10 years figuring this out. What happens is you have a hot carbon-bearing gas in the chamber, and you have a substrate, and on that substrate sits catalyst particles. Now, at the 1,000-degree temperature of CVD, the molecules of the gas strike the catalyst particle, break off a carbon, and it moves over and becomes part of a growing carbon nanotube. And the size of this determines like the size of the carbon nanotube in that. So that's great. Unfortunately, at the high temperature of the chemical vapor deposition, a whole bunch of other reactions are allowed, including junk carbon or amorphous carbon covering this, stopping the growth. Second thing is they found out that they thought the substrates, which are generally silicon, we're impervious to being penetrated by the callus particles, but at high temperature, they actually will sink down. This area will be too small to grow carbon nanotube. Final thing is Ostwald ripening. A thermodynamic process occurs. It essentially makes the large callus particles larger to the point where they stop growing carbon nanotubes because they're too large, and the smaller ones too small to grow carbon nanotubes. And the damage to the carbon nanotubes comes because they're cooking in this hot carbon-bearing gas this entire time, and reactions occur on their surface as well, thereby destroying their pristine structure. And so that's why carbon nanotube growth stops. It's very important to have long carbon nanotubes because they are essentially inert. When they're pristine, they're inert. The only way to get them to stick together is with these weak van der Waals forces. And the weak van der Waals forces occur between the surfaces, and it takes a long distance of lying against each other for that weak force to add up all its little components to be as strong as a bond between two carbon atoms. And so that's the optimum condition. Now, no one knows what that length is because they can't get carbon nanotubes long enough to actually do the measurements. One group tells me it's hundreds of microns. Another group believes it's a centimeter. So we'll see. So when I saw this presentation, I decided I would try. I'm an astrophysicist. They're material scientists. I don't know how important CVD is. I don't know the great impact it's had and how anyone would be foolish to try anything else, so I tried something else. In 2011, I heard about the problem. By 2013, I had developed 7 concepts, and 6 of those I'd already gotten rid of through deeper study. So I had 1 concept left. I raised some money, and I went into the laboratory, and in 16 months, I did 61 experiments, and I grew carbon nanotubes from experiment number 6 until about 61, maybe 60. And what I did was I just kept going, mapping out the parameter space of temperature and pressure and other important parameters that I could grow them in. So I have a robust way of growing carbon nanotubes in which the CVD problems should not exist. Now I'm raising money to do the next set is to grow carbon nanotubes longer, stronger, and in a configuration where they're really useful. That's what I'm trying to do. So in 2010, I came to the Mechanics of Slender Structures conference, and I've been busy since then. Oh, and this is important to me for Space Elevator because once carbon nanotubes have transformed our world, you know, we build everything differently, cars and electronics and aircraft and spacecraft and homes and bridges and elevator cables. As soon as we do all that, and we exploit the technology, we understand it, then we'll be able to build the space elevator. Because the space elevator is still the highest requirement of strength and lightness of material. And so it'll be at the end of our revolution here on the Earth, the carbon nanotube revolution on the Earth, that we'll actually be able to build the space elevator. So this space elevator, these are the initial parameters I'd like to talk about. So when Brad Edwards made his baseline scenario, he said it's 100,000 kilometers long, it'll be 1 meter wide in one direction, so you have something to grab onto to climb. In the other dimension, it may be as thin as a sheet of paper. It'll have a 20 metric ton capacity, which means he envisions putting 20 metric tons of tension on the whole ribbon. The ribbon itself, or the tether, will weigh 650 metric tons, and the counterweight will be 800 metric tons. Now, each climber would be like 7 metric tons of climber with a 13 metric ton payload. This is probably an overestimate because there was a dichotomy. He used like traditional materials to make the climber, whereas he would certainly, when they're ready to make climbers, I'm sure they'll make them out of super lightweight materials like carbon nanotubes. Power is beamed from the climbers to lasers, usually nominally near-infrared lasers that have some windows we can get through the atmosphere with little absorption. And because of the limitations on getting power to the climber, the first climbers will probably take 7 days to get to geosynchronous. The first elevator, now these numbers are in red because whenever I see a a scientist has estimated a cost of something, I always triple it because I know how good they are at estimating stuff. So $3,000 per kilogram is my guess. That's not that much better than rockets, but a couple things happen after the second elevator, and the third, and the fourth, and the fifth. So the estimate is the third elevator, or the fifth elevator, will actually be down to $300 per kilogram. And what's happening with that, the infrastructure of elevators making things less expensive, is that I'll explain after I explain this, the deployment scenario. So first elevator, you launch it, a spacecraft to low Earth orbit, and then once you assemble it, because it may take multiple launches, it'll be the biggest spacecraft we've ever launched. And then we will begin to power beam it, maybe using ion engines. We'll send power from the power beaming stations to it to get it up to geosynchronous orbit. From there, it'll start to deploy the tether downward. Now, the center of mass, scaled for the gravity well, will stay at geosynchronous. So the spacecraft will rise. This nice straight line is really an artist's conception. There's a lot of forces on it, and we have to have like a navigation module to keep it going and to take out the angular momentum that it needs to be reduced in order to get down to the Earth in a straight line. Eventually you make it, you touch this narrow ribbon to the surface, and this goes out to geosynchronous, and you start to climb with small climbers that you power beam up, adding a little bit of material at a time. And you do this for 2 years. So 2 years it takes to finish the first space elevator. And then its first job is to build the second space elevator with twice its capacity. So it would be a 40-ton ribbon. And then the second one's first job is to build the third one, which is an 80-ton ribbon. And then you can start using the first one for commerce. The other reason why it's very expensive is with one ribbon working and the other two building each other and stuff, it is cheaper to actually dispose of the climbers than to bring them back down. Once you have two operating, sending up payloads, then you can start bringing them down and the cost drops again. So that's why the fifth elevator is massive, takes up a lot of mass, a lot of spacecraft at a time, and let me see, it has a huge capacity, and that drops the price. In fact, we think using one elevator to make the other one means 70 trips. Instead of 2 years, just 70 trips up the elevator. And because of the way the gravity works and the force on the other side, you can put more climbers on than one at a time. So the challenges are many and varied. So we have nothing like climbers, which have to climb this ribbon for 100,000 kilometers reliably, at least 100,000 kilometers in the beginning, reliably, many hundreds of thousands otherwise. It starts in the troposphere, where we live, goes up high and goes through all these levels in the atmosphere, and ends up in space, traveling. So it's a spacecraft and it's a terrestrial craft. It's got to do all those things. So this is a real challenge. Power beaming is maybe not so much a challenge. We have high-powered lasers, even near infrared, through laser diodes. We also have, forget this free electron laser stuff, that's old. And we also have 12-meter telescopes, and we also have adaptive optics. But we don't have all three of them put together. So you do have to take these disparate things, put them all together in a system, and instrument the climber so that it provides a feedback loop to the adaptive optics system to make sure we can maintain most of the power on the climber. And of course, I've gone through these things. It's a problem how slow the first elevator will run and how low mass it can lift. We may not send people up on the first one because going through the radiation belt that slow, they would be radiation sick one pass through. And at the current level, we don't see any showstoppers, but we know that the devil's in the details. So we're always looking for showstoppers. And these are some of the hazards. We know that in the magnetosphere, the elevator cable will charge, and it's a charged entity, different charges, and it's moving through a magnetic field. So you'll get the classic Lorentz V cross B force pushing on the elevator. There's all kinds of induced oscillations that will help wear the ribbon, could make it go out of control. These things include, in fact, I'll skip those because I have them enumerated for this audience later. There's a level of Earth's upper atmosphere that is atomic oxygen. It's free atomic oxygen. And down here in the troposphere, lightning and wind are both big problems. We have meteors and space debris and other satellites, although as we put up more elevators, won't need satellites. But one of the things that I think this community could help us with now is that the space elevator community has a very simplistic view of the tether dynamics. So even though the material isn't exactly known yet, I can't tell you macroscopically what the properties of this ribbon are going to be. We can maybe get close. So any kind of analysis would have to be parametric. Still, it has a very high aspect ratio, a ribbon-like cross-section that is a complication. A constant tension tether is actually broadens as it goes up and is widest at geosynchronous and then gets thinner again. That's another complication to modeling this thing. There are also different boundary conditions. At the top, it's kind of a free boundary condition, but there is that massive counterweight or apex anchor. Down at the Earth, it's pretty much a fixed boundary condition. At geosynchronous, where we might have a station that could be used to put in dampening oscillations. It would probably be it's a free boundary condition, but yet you are pushing on a very large and very high tension cable. So what we're concerned about is these induced oscillations, which we don't understand very well, but you guys do. Our safety factor could be locally exceeded and the tether could be broken. Fatiguing of the tether over a lifetime will limit it. We have these chaotic motions. We have to probably move the reason it's on a floating platform is because it moves continuously down here. And in order to miss space debris in low Earth orbit. There's so much space debris, tether would be hit about once every 2 days. And fluctuations in the ribbon could actually affect the precision of launches from the ribbon. And we could fatigue the boundaries at the top and bottom, and that would, a failure like that would be very bad. So the sources of the perturbations are astronomical bodies. You know, every time it comes around, it sees the sun and the moon. And the moon is probably aperiodic because of the way it moves. The sun's pretty much periodic, so it can be a driven oscillation. The Lorentz force, I've already mentioned, just ascending and descending the ribbon with a tether. It's constantly changing the angular momentum of that climber, and that can induce oscillations. All kinds of collisions, including launches. Launches, in a sense, are an inelastic collision run backward. Solar heating and cooling. We know that the elevator near the Earth would be eclipsed every day, or every night, I should say. Every night, and when it comes back out, there'll be a thermal shock. And the motion of the ground station to avoid debris and wind. Wind on the Earth will propagate upward, the oscillations will propagate upward. And we need sensors for position knowledge to be able to damp, and a calculation to tell us how and when to damp. And we don't want to get into any kind of chaotic motion, which would be very hard to figure out how to damp. So, ISEC is the nonprofit 501c3, the International Space Elevator Consortium. If you're interested to join this, there's our website. This is our fearless leader, Peter Swan. He's the president of ISEC. We have conferences every year near Seattle, Washington. The next one will be in August of 2019. David Horn puts it on. You can see details on this. Really hard to remember, spaceelevatorconference.org. And so my conclusion is that we humans can be a spacefaring race. But for where I'm standing, we have to build a space elevator to do it. And what could be better to spend your time on? Because after all, now in the 21st century, we're writing the history of the 20th. And it's clear to most people that one of the best things we did in the 20th century is to land men on the moon. When they write the history of the 21st century, they're going to say, one of the best things we did was to build the space elevator. Thank you.